Hello, my name is Steve Branham. I'm a software engineer with a focus on embedded systems development, primarily for communication systems, but also for IoT devices. I have 40 years of experience developing software, working on a variety of products, from network routers to consumer products. My IoT experience is primarily on the device side, but also on the server side. It includes working at Sonos, SimpliSafe, iRobot, Verizon Wireless, and I've just started a new job at Motional, working on self-driving vehicles. That perhaps stretches the meaning of IoT, but robotic cars share many characteristics with IoT. I'm going to present some considerations for working on IoT systems. My goal is to highlight some potential problem areas and recommend practices for avoiding them. Some of this may seem obvious. I would expect that none of it is news to mature organizations, so this is intended primarily for those who haven't reached that level. IoT requires rigorous and disciplined engineering for long-term success. I'll set the context first with IoT characteristics. Then I'll move into some problem areas that you might run into. You might experience these directly or in some variation. Then I'll cover some solutions. I'm guided by three principles. From Pasteur, chance favors the prepared mind. By preparing you to watch for these things, I hope that you'll be better able to deal with them or prevent them. From Santayana, those who do not remember the past are condemned to repeat it. Learn from the mistakes of others. Maybe you'll be able to avoid them. And for me, trust nothing and verify. You need to have an appropriate level of paranoia so that you verify and confirm everything. Don't just trust that it will work, no matter who it comes from, even if it's your own code, even if it worked before. We have many ways of tripping ourselves up. Let's look at IoT characteristics. This breaks down into two areas: system characteristics, the technical characteristics, and project characteristics, the management characteristics. These are some of the system characteristics, the technical aspects. The IoT triad is a set of three primary components that interact to form an IoT system. An IoT system is a form of distributed system. Embedded devices have a number of their own complexities even without IoT, as do front-end apps and back-end servers. The IoT triad consists of the three components that make up an IoT system: the devices, the apps, and the servers. The embedded device things are the physical product that customers buy and use directly. These are the things of the IoT. These are embedded systems, meaning a computer is embedded inside a specific functional item. You don't think of it as a computer, you think of it as that functional item, like a security camera or a thermostat. The front-end apps are the mobile, desktop, and web applications that customers use to interact with those devices. They run on smartphones and other mobile devices, on desktops, and in browsers. These are the user interface to the embedded device things. The back-end servers are the company systems that interact with the devices and the apps, these days probably running in the cloud. There might actually be multiple different servers involved, either monolithic systems or microservices. These may interact with additional third-party systems. The public internet is what connects the apps and devices to the back end. The apps and devices may be able to communicate with each other directly over a local link, but that's not always the case. If not, they can only communicate indirectly through the back end. The apps and devices run in the customer environment, on their premises and their equipment. Once in the hands of customers, companies will have limited physical access to them. The back end runs in the company environment, on its premises and equipment, or in its cloud instances. If an app has a direct link with the devices, they can communicate with each other directly, without necessarily involving the back end. But if not, They must go through the backend even when physically right next to each other. So a smartphone in the same room with the device may need to route all its communications through the backend, which could be on the other side of the country. IoT systems are a form of distributed system, where each of the components contributes some of the functionality to the final product. Each of the three components of the triad must work in coordination with the others. They must conform to the application-level protocols that form the various functional workflows. Each component has its own inherent complexities. The need for coordination further complicates these. Poorly coordinated components create havoc and consume large amounts of time during development and operations. Each component must be robust in the face of incorrect behavior in another, whether due to bugs, poor coordination, or poor communications. Communications are inherently messy and unreliable. Messages can be lost, misdirected, duplicated, or corrupted. Outages range from momentary transients to long-term disruptions, from degraded throughput to total failure. Many parties are involved along the paths between components, involving many hardware and software elements, mixed in with large volumes of other traffic. There are many opportunities for things to go wrong. The Internet is not a friendly place. There are bad actors on the Internet who seek to disrupt or break into communications for a variety of motives. All communication ports are potential entry points, subject to a constant barrage of attack. Naive trust will be punished. Remember, trust nothing, no matter where it came from, and verify. Let's take a quick look at the complexities of each of the components in the triad, starting with the embedded devices. These are typically constrained in multiple dimensions. They often have limited CPU performance, limited memory, and may have power limitations, especially if they're battery powered. All these items affect BOM cost, which translates to customer cost. They may also have hard real-time requirements, meaning they have to act within a specified response time, or something will fail functionally. Communications may be limited to certain channels, such as wired, Wi-Fi, Bluetooth, or cellular. Bandwidth and buffer capacity may be limited. Network stacks may have limited capabilities. Communication latencies or errors may interfere with proper operations, to the point of being unsafe. Devices may have safety requirements, all the way up to critical life safety. Devices must operate securely, meaning they must be protected from unauthorized access, unauthorized use, and running unauthorized code. They must protect customer data. Poorly secured devices have been used in several notable DDoS attacks. Devices must run reliably for long periods of time. This can be measured in months to years. They must be robust in the face of communication failures and user mistakes. Depending on the device, they may also need to be robust or have a safe state in the face of hardware failures. Devices may use specialized hardware. This may require specialized skills for hardware and software development. Third-party libraries may be included in the software. While this can speed development, it also risks delays if the libraries have problems and are poorly supported. Devices may have update capabilities, such as OTA, over-the-air update. OTA needs to be rock solid on both the device side and the server side, because there may not be any other way to fix problems on customer devices other than shipping them back. That has the potential to be a customer service, logistics, and financial disaster. The front-end apps have their own complexities. The primary complexity for front-end apps is the user experience. The apps represent the user interface, the part of the IoT system users can see and interact with. Designing good user interfaces can be difficult. Apps must be responsive. Apps that don't provide effective feedback quickly are frustrating. The user doesn't know if things are even working. There may be times when the user is trying to control the device in a stressful situation where they may be impatient and distracted. A complex app risks mode confusion, where the user doesn't know what to click on or loses track of where they are in an operation. Poor general usability is extremely frustrating. If the app doesn't work well, in the user's eyes, the embedded device doesn't work well. The IoT product doesn't work well. Apps may have communication limitations similar to the embedded devices, with only certain channels available, and without a direct link to the devices. Apps must be secure in their communications and in the data they store locally. They run on devices that have other apps installed, possibly malicious ones. They may use PII, personally identifiable information, that includes credentials and financial information. The functional application data generated by the IoT device must be protected, such as video or data streams. The commands issued to the device or backend must be secure. Apps must be reliable. They mustn't crash or corrupt data. They must behave reasonably in the face of incorrect user input and communication issues. Apps have to be able to run on a range of mobile and desktop devices, presenting a reasonably consistent user experience across each of them. Like embedded devices, apps may use third-party libraries with the same benefits and risks. Apps have update capability and also must deal with updates to the underlying platforms they run on. That includes the potential that some features of the platform that an app relies on is no longer supported. The back-end servers also have their own complexities. Scaling is a major source of complexity for back-end servers. They may need to work with millions of apps and embedded devices. This creates connection load, computation load, and data load. Every order of magnitude growth results in new pain points. Things that worked at lower scale may fail unexpectedly at higher scale. Closely tied to scaling is performance. What is the CPU and resource consumption per connection and per workflow? How does it perform under load, if many of the apps and devices interact with it at once? The backend must be secure, both in its communications and its data storage. Because of its concentration of data and control, it makes a tempting target for malicious actors. The backend must be reliable. A single process failure can affect a large number of customers. How is functionality of the app and remote devices impaired, and for how long? What backup or standby capabilities are in place? Servers may also use third-party libraries, again with the same benefits and risks. Servers can generally be updated fairly easily, but that must be managed operationally to maintain customer functionality during updates for all the apps and devices that are interacting with them. Controlled load shedding and ramping can maintain stability. Conversely, servers also need to be able to deal with the fact that apps and devices won't all update uniformly, so there will be multiple different versions of them running in the field. That situation may persist for a long time. These are some of the project characteristics, the non-technical management aspects. The project will have a life cycle over its full life, from conception through retirement, which can be many years. Development is often done by separate teams. The project must have several abilities in mind to be successful. Each of the components individually has a life cycle, as does the system as a whole, whether it's an agile model or something else. This starts with development, which breaks down into some form of requirements, design, implementation, testing, and maintenance. Then it moves to deployment, fielding running components and getting things operational. From there it moves to operations. This is the long-term phase. This is what drives revenue, either directly through service subscriptions or by motivating sales of the devices. There are different timescales for each component. Then for new versions, there will be multiple overlapping cycles over the total product and company life. This is for the long term. It isn't just about getting to Gen 1 v1.0, but about getting to Gen 10 v12.0. It's common to have separate development teams for each of the triad components. Those teams will probably work in different languages. They'll have different tool sets. They'll have different development practices. They'll have different runtime environments. They'll use different deployment methods. They'll have different scaling and performance requirements. These all call for different skill sets. Most significantly, they may have different schedules and priorities, which sets the stage for one of the problems we'll come to. Overall, the project must have a number of abilities in mind that affect the way the system is built. These are the qualitative attributes you need to build in from the start, from both an operational and a development standpoint. The code must be readable so that new people can work on it. It must be maintainable in order to have a long life. It must be testable so that behavior can be verified before customers stumble into problems. It must be debuggable so that problems can be investigated. The system must be monitorable so you can assess its operation. It must be controllable in all conditions, including exceptional and problem situations. It must be able to survive whatever happens to it. This is robustness, handling not just the happy paths and the happy days, but also the unhappy paths and the unhappy days. Now let's look at some problem areas. The problems I'll talk about here are project coordination among the development teams, testing at various levels, automation, primarily the lack of it, runtime environments, where the components run throughout the lifecycle, documentation, again, the lack of it. Let's start with project coordination. Lack of coordination between teams is one of the biggest potential problems. This can be very disruptive to the overall project, resulting in chaos that causes delays, missed schedules, and customer problems. The teams might have different feature support at a given time. One team supports features A and B, while another supports B and C. For instance, what if the app and the device support setting a scheduled time to turn it on, but the server doesn't support that yet? Teams might implement behaviors differently from what the others expected. What if the app expects the device to turn off automatically, but the device expects a command to turn it off? Teams might implement messages and data differently from each other. What if the app sends a duration in minutes for the device to run, but the device expects a stop time, in Unix epoch form? This causes fragmented capability in the system because there's not a consistent end-to-end workflow. When QA tries to test these features, none of them work. This causes problems that consume a large amount of time collecting and analyzing data for bugs. QA spends time creating bug reports, and developers spend time investigating them, not realizing the differences between the components. Good testing is a challenge across all the IoT components. The distributed nature of IoT just complicates that. Premature end-to-end testing before all the components are ready is a recipe for frustration. Insufficient end-to-end testing is also a recipe for failure. There are a lot of moving parts. When things don't work right, is it because of something you did in one component or something someone else did in another component? Or is it due to something in the internet or the local network? There are lots of things that can go wrong during testing. Triaging and chasing down failures can be time-consuming. You need to be able to isolate things and control the test environment. You need to be able to test even if peer components aren't ready yet or are unstable. You need to be able to test the unhappy paths that are hard to trigger. You need to be able to test reproducibly and deterministically. You need ways to build confidence in each piece step by step, and then end-to-end. Working on an IoT system requires a lot of procedures throughout the lifecycle. Many of these will be manual, especially while they're first being worked out. If they aren't automated, they become a source of problems. Manual procedures are error-prone, subject to mistakes. That makes it hard to troubleshoot when things aren't working as expected. Because of that, they aren't reproducible. That makes it hard for other people to follow them. They're time-consuming and often tedious, which makes them even more error-prone. They're difficult to document if steps are vague. All of this makes them fodder for the journal of irreproducible results. The runtime environment needs are different for different stages of the life cycle. Developers need an environment where they can work without getting in each other's way. Once the system is running in production, they need to be able to work on new versions without affecting that running system. Testing has similar needs. Some types of testing may require unusual environments. When preparing to deploy a system for production, there needs to be a place where everything can be set up. If it's a new version of what's running in production, it needs to be done where it won't affect any currently running production system. Once a system has been deployed and is running in production, it needs to be isolated and protected from all other activities. Don't test in production. This will get your company into the news where millions of people can see it. But I don't mean the good news. This is a great way to DOS yourself. Oh, sorry, we crashed the server because we were testing a new device version. Customers can't control their devices. You risk corrupting production data. Oh, sorry, while testing a new microservice, we deleted all the customers whose names start with B from the database. You risk privacy violations. Oh, sorry, we expose customer PII to the QA testers. Or worse, sorry, the server we were testing allowed customers to see each other's data. That will really get you into hot water. You risk creating security holes, allowing malicious actors into your system. Oh, sorry, we had to disable the firewall temporarily to get the test to run, and someone got in and copied off the database. You risk disrupting customers and the revenue stream. Oh, sorry, we lost service to North America when the test crashed the server, and we had to issue refunds to everybody. This risks long-term reputational damage in the marketplace. Will customers want to use your product? Will investors want to invest in your company? See the movie War Games for an example of why not to test in production. Real systems and real data do not mix well with tests. Production is the crown jewel. Protect it. Don't mess with it. Documentation is a perennial problem with IoT development, just as with other types of projects. Everyone seems to be so afraid of documentation. It's so much work. It gets out of date. No one reads it. As a result, projects often suffer from a lack of it. The problem is that on a distributed system like this, there are many interactions between the components that have to be understood by the different teams. There are lots of opportunities to make mistakes. Again, this is a coordination issue. Without documentation, there's no authoritative reference for what is intended. There's no explanation for how things fit together or are supposed to work. That leads to confusion and misunderstanding, with people doing the wrong things. The resulting chaos consumes large amounts of time chasing down and sorting out the issues. When a new person joins the project, what are they to do? They'll have to spend time piecing things together from obscure clues. The code is the documentation, but what if it's not even clear what the code is for, or what it's trying to achieve, or how things work together? What if the code is just wrong? The meaning is buried under the weight of all the details in the code. That increases cognitive burden, which slows down understanding. Now let's look at some solutions for those problems. These address the set of problem areas we just looked at. To address lack of coordination, you need somebody who can be a total project coordinator. This person needs to have cross-team responsibility and authority for seeing that end-to-end workflows are implemented. That means they need to have decision authority. Call this person whatever makes sense for your management structure. They'll be the one who prioritizes workflows. Then they'll coordinate the activity of the various teams to execute on those priorities. They'll verify the results of the activities. They'll be the central maintainer of the data model and message dictionary. They'll be the arbiter for questions and disputes. They'll be responsible for acceptance testing, seeing that tests are created, that they get executed, and that the system passes them. It's a bit of a complicated role because it requires a mix of management skills and technical skills. It requires the trust and respect of the teams. This can be hard-won, yet easily lost. This person doesn't work in a vacuum, managing by fiat. They need to work collaboratively, in consultation with the teams and other project stakeholders. Test-driven development is the first stage of good testing. You can use it individually for each of the triad components, the embedded devices, the front-end apps, and the back-end servers. It's a very effective unit testing strategy with many benefits. Break down each component into constituent parts for development. Each part is a unit. These are then tested in real time by the developers as they are working on them, when the work is fresh in their minds. This creates a fast feedback loop. It identifies and fixes bugs quickly before they affect other people's work, other units, and other components. Mocks and fakes stand in for the things a unit interacts with, allowing you to control their behavior. That allows you to test a part in the absence of other parts. If one or both of the other components in the triad isn't ready yet, you can still do testing of the parts that make up your component. You can test all possible paths, even the unusual dark corners that are hard to exercise in other ways. This gives you provable test results, which builds confidence in the code. Once working, these unit tests provide a safety net for making changes and catching regressions. That maintains confidence. Are you worried about writing double code? Don't. You needed to put some kind of effort into testing anyway. TDD produces working code and usable regression tests that also act as example code and significantly reduces or even eliminates the debugging phase. This test code is very valuable, just as valuable as the production code. Once you have the units tested, you need to test whole components. Here the units have been integrated and are interacting with each other, driven by messages. Message simulators are the next stage. They extend the concept of TDD out from the unit level to the triad component level. These are the green circles you see here inserted into the communication paths, terminating each link. You run the real code in the component, and the simulators act as controllable mock or fake stand-ins, simulating one or both of the peers. They might actually be running on the same system as the real component or on a separate system. They act as message sources, message sinks, as initiators, and responders. You can use any combination of real links and simulated components. For instance, now showing a real app and device communicating over a real link, and both communicating with back-end simulators. The back-end has been cut out, so the apps and devices can run without it for now. The simulators decouple components from their peers for development and testing. They can be scaled to different numbers of instances as necessary. Need to test a server under the load of tens of thousands of embedded devices? You can do that easily, long before any devices are ready. You can set up controlled failure scenarios, like slow or unexpected responses, poor connections, or malformed or corrupted messages. These also serve as validators for correct behavior, giving you a known reference point. You can script scenarios to isolate failures or prove that things are working as expected. You do need to balance the costs of development and maintenance with the benefits. You especially need to be sure the simulators accurately model messages and sequences. But again, the arguments for TDD apply. Automate everything that can be automated so that it's easy to do and is reproducible. You want to have push-button operations. Someone just needs to push a button or enter a single command to carry out an operation. There are a variety of things you can automate. Setting up the development environment so that each developer has a closely matching functional work setup. That way they don't have to waste a lot of time manually installing things and setting them up. And they don't make any mistakes that cause mysterious problems down the line. Running builds of all types. This is both for individual developer local builds and CI/CD builds. Setting up a runtime environment and performing deployment. For things that run in the cloud, this includes spinning up cloud instances and resources. Performing log analysis. IoT systems can produce large amounts of logging very fast. This can be time-consuming, tedious, and extremely error-prone to examine and evaluate. Any tools you can build to speed that up will pay themselves back over time. Generating analytics for operations management, and generating alerts from monitoring. Automation is critical for testing at all levels and for all types. In addition to aiding the discipline of repeatability and thoroughness, it helps with the basic discipline of ensuring that tests actually get run and evaluated. Without automation, it's too easy to skip them. This is the unit testing we covered in TDD to make sure each unit is thoroughly shaken out on its own. If the code can do it, make sure there's a test that covers it, even if the larger system doesn't currently exercise that path. If you do TDD, you're all but done for unit testing. Just be sure to incorporate the tests into the automated builds and fail a build that fails a unit test. Likewise, TDD and incorporating the tests into the builds has done most of the work for regression testing. If you find a new bug, make sure you add a test for it, and whatever test suite is able to check for it. Use those message simulators and other integration test methods where you can script the configuration, set up the test scenarios, and run the tests. Automate the setup, running, and evaluation of tests to provide pass-fail acceptance criteria for units, integrated subsystems, and full systems. System testing is end-to-end testing, using real components as much as possible. Automate the setup, running, and evaluation of tests to provide pass-fail results or collect data. Functional testing verifies that things function properly in each of the currently implemented use cases. Performance testing collects characterization data on a number of performance metrics under a variety of conditions, from idle to normal operation to heavy load, and for various use cases. Load testing collects data on performance metrics under specific load conditions, especially when exploring system limits and scaling. Security testing tests various security attacks and conditions, as well as modeling DDoS scenarios. Set up multiple end-to-end environments for the various lifecycle needs, each isolated from the others. Set up separate development environments where developers can run their code, safe from each other and safe from production. Provide test data for the developers to use. They might be able to share environments, or you might need one per developer. Set up separate test environments where testers can run their tests, again safe from each other in production. These might need to be customizable to set up different operating conditions and scenarios, and using different test data sets. Set up a staging environment where you can stage a production rollout. Here you can set up everything and verify it's ready to go online. You might use this as part of a phased rollout using expanding phases or regional phases. Finally, set up the production environment, that crown jewel that is safe from what everyone else is doing. This is a lot of work and a lot of details to keep the different requirements straight. That's where automation comes in, to assist with setting up and managing all these. Again, ease of use and reproducibility are huge benefits. To address the problem of documentation, write stuff down. That allows information sharing between individuals, across teams, and across time. Good documentation serves as the authoritative reference for what is intended. It helps navigate a system quickly in different dimensions, providing maps into the codebase. The discipline of writing things down forces you to think things through. It forces you to gather your thoughts and organize them. It forces you to explore details, then to abstract and distill meaning. Forethought is a good thing, even if you change your mind later. Investing the time and effort to write and maintain documentation can save you time, because it helps avoid confusion and missteps. This is part of being a disciplined engineer. That investment also helps reduce the chaos that can drive frustrated developers away. Find the right balance. We've seen that overwhelming, voluminous documentation is the wrong answer, but zero documentation is also the wrong answer. Find something that's light yet conveys useful information. Versioning is important because you'll change it over time. The ideal I'm striving for is that if a new person joined the project, you could direct them to this documentation, and they would be able to start working in the codebase knowledgeably, effectively, and safely as a result. Think about it in those terms. What would they need to know to make them effective, and to make sure they work in coordination with everyone else? Then all that information serves as the authoritative record. Everyone has a uniform reference. If someone needs some details because they forgot or they need to know about another part of the project, they have a place to go. Let's look at what's useful for system-level documentation. System architecture diagrams identify the various elements that make up the components of the triad and how they interface to each other. There are probably multiple different views that are useful. Use the single sheet rule, meaning a given diagram fits on a single sheet of paper. Use hierarchical diagrams to zoom down to the next level of detail, like a set of maps that zoom down from the level of continent to the blocks on a street. Actor roles outline each of the customer, support, operations, and administrative actors who interact with the system, identifying what elements they have access to and what they're authorized to do. Anyone who touches the system in any way must do so within a defined role, because that will lead to the definition of use cases and messages. Remember that there are times when someone will need exceptional access and control to deal with exceptional situations, so plan for those. Use cases outline each of the uses of the system by the various actor roles, identifying what elements and other actors are affected and how. This includes cases that are triggered asynchronously by the triad components, for instance when they detect some condition. In addition to normal use cases, remember that there will be exceptional situations that need to be handled. Data models and schemas outline the data that's managed by the system for both short and long-term use, and data both in flight and at rest. The message dictionary outlines all the messages exchanged by the components, identifying which use cases they support, which components they involve, and which data model items they use. Sequence diagrams illustrate the message sequences and workflows for each use case, showing which messages are exchanged by which triad components and in which order. They may also show asynchronous events that trigger activity. The theory of operations is how you would explain things to someone while standing at a whiteboard. Don't get all wrapped up in formality. What are the key things you would explain to someone so they could work on the system? This is your narrative explanation, where you can tie things together. How deep you make it is up to you. You can reference the other documents for the details. There's additional documentation that's useful for each of the individual components. This is unit-level documentation, corresponding to the units that you broke down for unit testing. State transition diagrams detail the behavior of event-driven or stateful units. Data structure diagrams show the layout and relationships of data structures, including non-volatile or persistent storage. Class diagrams show the layout and relationships of classes. Call trees show the sequence of function calls for specific use cases, conveying information similar to sequence diagrams. Debugger backtraces can be useful for capturing these. Alternatively, You may prefer sequence diagrams here as well. API and internal programming interface documentation is reference information that documents the API and the internal interface for a unit. Automated tools such as Doxygen can help gather this from annotated code. The unit tests are actually functioning code examples showing how to use the code. They serve as another form of API documentation. Like the system-level document, the unit-level theory of operations is a narrative explanation, how you would explain the unit to someone while standing at a whiteboard. Watch out for these and similar problem areas. I hope that by being prepared, you'll be able to avoid them. Thank you for watching.